Let's get moving. If everybody could quiet down, we'll go ahead and get started then. Thank you. All right, so I'm Adam. I work with Unity Technologies. I'm going to be talking today about getting started with physics in our data-oriented tech stack. Before I get going, I want to give you all an overview of what the topics will be, so you maybe have a sense of what to expect here, and then also to know if maybe the things that you're hoping to get out of this might be better covered by a different session later. So to start off with, I'm going to be talking about why we made Unity Physics, and I'm going to get behind the partnership that we have with Havok and kind of the differentiation between Unity Physics and Havok Physics and how those work together, and a little bit about our design objectives behind Unity Physics. So if anyone was at GDC and saw the talk that Rory Mullane from Havok gave at our booth, that'll be a lot of similar information. After that, I'm going to talk about some details of the actual runtime systems and the runtime data protocol, and then finish up by talking about the game object conversion workflows that we have right now for building kind of optimal collision setups and taking advantage of some of the new features that we offer with Unity Physics and Havok Physics. And then at the end, I'll kind of have a few slides about our near-term roadmap to give you a sense of what we're going to be working on over the next 6 months, 8 months, something like that. So before I get going, I'd like a show of hands here. Is there anyone in this room who is using either Unity Physics or Havok Physics today with dots? Okay, there's a couple of you. How many people are using dots, but you haven't started using Unity Physics yet? All right, and how many of you kind of have no clear idea yet of what dots is or what it means for you, or you're just getting started? I'm assuming everybody else, and the rest of you, you're not telling me why you're here. Great. So I'd like to let you know, too, about a couple other sessions that you might be interested in based on which of these groups you fall into. So immediately after this talk in this room, one of our colleagues from Havok is going to be giving a talk specifically about Havok Physics in Unity and sort of how the performance and behavior characteristics differ between the Unity Physics and Havok Physics simulation. At the same time, in a different room, there's going to be a session on kind of the low-level details about converting scene data to dots. So if you want to understand some of the minutiae of how the game object conversion pipeline works, that might be an interesting talk for you. There's also a talk on our animation rigging tools for Unity 2019.3. I mention that because it tenuously relates to some of the things that we're going to be doing in the future with physics. So anybody who's maybe interested in how physics might relate to animation and characters, you might find that useful. And then finally, at 3 o'clock today, Nicolina and Chartan are going to be giving a talk unboxing dots that really is breaking down our thinking behind the design of our workflows around dots content and so forth. So again, just depending on where your interests lie, I think any one of these could be valuable for you. And I also want to give a pitch for roundtables that we're going to be doing. So we have a few open slots. If this is something that is interesting to you, then let me know after the session or find my product manager. I'm sure he's in the room here somewhere, Sean. But today at 3, we're going to be having a roundtable about character effects and physics-based animation, and then tomorrow one about physics for artists and designers. So if you're coming from, let's say, a studio where you have some very specific needs related to physics and animation or how your level designers are setting up physics, we would love to hear from you and get some feedback in terms of what we're planning to do and how we can meet your needs. All right, so now let's start actually talking about physics. Why do we need more physics engines in Unity? Today we have sort of our classic GameObject-based 3D physics engine built on PhysX. We have Box2D for the 2D content, and then we're talking now about adding 2 more physics engines for dots, right? So why did we need to do this to sort of move forward? The idea is that we want dots to really be a foundation for an engine that can last well into the next 10 years. And so part of that is thinking about what are the needs that people's games and productions will have with future technology. So part of that relates to connectivity, right? We understand that there's a need for a variety of different networking architectures. So you might have your standard sort of first-person shooter type of game where you've got server authoritative with lag compensation and all that. But we might also want to enable things like having 2 clients move in lockstep, or we want to do GGPO, where you do rollback for a fighting game, for example. And so accomplishing that with existing physics solutions today is pretty challenging. Likewise, if we're thinking about connectivity, a big part of the future relates to cross-architecture determinism, right? We're going to have people playing the same game potentially on tablets, on different mobile phones with different processors, PC, consoles, and so on. And in order to enable all these different networking models with cross-play, we need to be able to execute deterministically across these different types of hardware. And we also want to scale sort of to the very small and the very large. So if you think about Unity today, sort of the classic game object-based approach, it wouldn't really scale down very well to, let's say, the sort of instant games, things that need to load in under 500 milliseconds, or up to the extremely large, maybe open world types of games that you see on consoles. So we want to try to make sure we're hitting all of these beats. So we thought, why don't we build a stateless physics engine using high-performance C# and burst, right? So how does this actually stack up for our needs? So if you have a stateless physics engine, this is ready for all the different types of networking architecture you might have. So for like a fighting game where you need to roll back, you can just say to the client, like, oh, you're actually here, all of these bodies are at these positions and they have these velocities, and now you proceed simulating. If you have a stateful physics engine where you're achieving performance with caching, that's more complicated to pull off. You might need to warm up the caches or something, or it may not even be possible. Similarly, if we're building on top of burst, burst is going to be the tool by which we achieve cross-architecture determinism. And so if we build a stateless physics engine on top of that, then as that becomes ready, it's something that we'll be able to take advantage of from a physics standpoint. The question, though, is whether this can scale to the very large scenario, right? So if you have a stateless physics engine, you don't have bodies going to sleep, for example, and so it may not be well suited to sort of large-scale open-world environments. How are we going to solve that problem? And we thought, well, why don't we actually find some people who are experts with large-scale game physics? And better yet, we can let them do all the hard stuff for us. No, I mean that in jest, but really, we couldn't have imagined a better partner to carry this forward than Havok. They have a tremendous amount of experience in high-performance game physics, and they were ready to tackle the challenge of building this stateless physics engine with us, and doing this in a way that would ultimately allow our users to have access to 2 different physics solutions based on their needs. So this is the way by which our users now can also take advantage of Havok Physics. So the way that this is done is we have these 2 physics engines that are compatible with DOTS now. There's Unity Physics and Havok Physics. Unity Physics is the one that is stateless and is built on C# and burst to sort of satisfy those requirements that we had initially laid out. And we feel that this should actually meet the needs for a vast majority of games. Havok, on the other hand, achieves a tremendous performance improvement and stability improvements in the solver by relying on caching and a lot of other optimization techniques that they've perfected. But you get sort of more stable and high-performance simulation in large environments in this case. So I want to unpack this concept of what we think a vast majority of games actually need, because this can maybe sound controversial to people. They might react and say, well, you have a physics engine here that doesn't actually implement stable stacking. How can you say that that meets the needs of a vast majority of games? So when we're thinking about the vast majority of games, we're thinking about kind of the whole spectrum of content that people build with Unity, right? So you have things like card games and puzzle games that they don't actually need a generic physics system or spatial querying system. You have maybe objects or tiles operating on a grid, or you're just testing mouse positions inside of a rectangle. So that's actually a huge number of games that are built on Unity. And as you kind of move up here, the first sort of entry point that you have into needing a generic physics solution is really just optimal static queries, right? So querying static geometry in a 3D world. So I highlighted here the image of our FPS sample because I want to point out that the entirety of that game for the core gameplay is just a character controller moving around static geometry. You know, we've got ragdolls for secondary effects and stuff like that. But the same is true, actually, of the dot sample that was shown during the keynote. There's actually a lot that you can do with just a collision world and querying in that space and moving around a character. As you start to move up, though, and maybe you need ragdolls or projectiles or something like that, you start entering the space where you have to think about the actual performance and behavior characteristics that are required of your game. So, you know, if you get into the space of falling down stairs or marble runs or things like that, In some cases, Unity Physics might be a suitable solution for you, but there are other cases where opting into Havok Physics will be the thing that actually unlocks this production for you. And then if you move into the more specialized use cases where things like stable stacking really become important is if you have, let's say, a game like Jenga or Boom Blocks, right, where the game fundamentally relies on having stable stacking for the puzzles to even work. So in terms of our design objectives for Unity Physics, right, we want to make something that's going to solve these use cases that we have for connected games, but also sort of service a large number of games. We wanted to build something that sort of your somebody who's maybe an enterprising developer can go into the source code, look at it, understand it, and maybe even make modifications if they need to without having to worry about all the caching mechanisms and how that might interfere with the changes that they're making. So part of the way that we do that as well is that we have this common low-level physics data protocol. So the idea here, the goal, is that you should be able to ultimately substitute in even different simulation backends if you need to. So if you imagine you have a game where maybe Unity Physics or Havok Physics solves for the majority of your use cases, but you have some particular part of some particular level where you have maybe a really long chain of bodies with really irregular mass ratios, and you need a custom solver to do that. The idea here is that you should be able to slot in your own physics solver to solve those types of problems. Or if you need something that's altogether different for industrial simulation or whatever, that you should have that option. So the goal in the long term here is really to make this something that is as extensible as possible without requiring that people modify the source. And part of the way that we hope to accomplish that is by inviting people like you to reach out to us in the forums and help us kind of flesh this out and move it forward and make sure that we're actually making good on that. You know, so today we think that that's generally true in the sense that we have two very compelling physics offerings that are able to work with this. So when we talk about this common low-level data protocol, what we really mean here is these bits in these highlighted yellow boxes here, this collision world and dynamics world. So if you think about starting over at the very far left, we have your entity data. So in the world of dots, this is your runtime components, right? So translation, rotation, physics, mass, and so on and so forth. We have this BuildPhysics World system that ingests those entity data and then rearranges them in a way that's optimal for solving physics. And so part of that is that we have these bodies in the collision world as well as the motion data in the dynamics world. And then we can reuse this collision world for either solver right now. So because we get tremendously fast raycasts with the bursted version of the collision world here, we can use that for either Havok or for Unity. And then when we actually simulate the dynamic entities, we just take a look at which backend are we using, and we'll switch on one of those, and then we export all of the results back to the entity data. So we're writing out positions and rotations back to the bodies. But you know, the idea here is that your physics could go in here too, if you needed to for some reason. All right, so as I start to dig into details, I want to remind everybody that DOTS is still in preview, and in particular for anybody who might be watching this online later. Today is, I think, September 24th, 2019. If you're watching this in 3 months, 6 months, you know, names of things might have changed. Some of the specific recommendations might have changed, but all the high-level concepts should still be valid, right? So maybe the way that you actually build some particular type of content will have some different steps involved, but the gist is still intact. So with that out of the way, I want to start by talking about the entity data protocol. So this is the physics runtime. So in the world of dots, compared to, let's say, monobehavior, we have a lot more granularity in our component types because the idea is that you want to operate on sort of the minimal set of data that you actually require in order to do some sort of operation. So we've really sort of decomposed these aspects of physical bodies into a number of different components. But chief among these are physics collider and physics velocity. And these are sort of the minimal criteria for things to be considered part of the physics simulation or part of the collision world, as the case may be. But if you look at like the mass component even, this isn't just the mass value itself. This contains sort of the inertia frame and some like the center of mass offset and so forth. But we've got, you know, damping per body gravity factor as well as these custom tags. So if you're writing code in a high performance code path and you just need to test a particular bit on this body as opposed to reaching into the entity manager and doing a random access and so on, that's one avenue that you have for doing this. So in terms of the actual main runtime systems, we've got the BuildPhysics World, StepPhysics World, ExportPhysics World, and then this final sort of catch-all in-frame physics system. And one common feature of all of these is that they have this sort of final job handle exposed. So the idea is that if you have some job that you want to execute, let's say after you've built the physics world, you maybe want to be querying against the static geometry, and that can happen in parallel with the simulation, because you know that the stuff that you're querying against isn't going to be moving. You just need to make sure that you not only update after the BuildPhysics World, but that your job has a dependency on the BuildPhysics World final job handle. And as I alluded to before, kind of the two key products here of the BuildPhysics World step are this collision world and the dynamics world. So in terms of the BuildPhysics World, we have three sort of key query groups right now. So we have dynamic entities, static entities, and joints. The chief difference between dynamic and static entities is the presence or absence of physics velocity. So if something has translation, rotation, and velocity, it is a dynamic entity. It may or may not have a collider. It's fine, we can still simulate it either way. And then respectively, static entities require a collider, translation, and rotation, and they must not have a physics velocity. So anything that satisfies those criteria, it's part of the static collision world. And then joints are just individual entities that describe a constraint, and then two entities that are constrained by that relationship. So that's sort of in contrast to the monobehavior model where you had a joint as a component on one of the bodies maybe. The idea here is this is an altogether separate entity that's describing two other entities that are constrained to one another. So there's also some more advanced stuff in here, depending upon how deep you want to go. We have, if you think about cutting up the physics system into broad phase, so you're just getting overlapping pairs of bodies, the narrow phase where you're generating contact points, and the solver where you're integrating and applying constraints and so forth. We have different custom job types where you can actually sort of inject in between these systems to make modifications. And this is really important if you're doing, let's say, like a racing game, for example. You might need to do some modifications at a very low level in order to achieve the types of behaviors that you would expect in those scenarios. So for example, you can create an eye-body pairs job that would execute between the broad phase and narrow phase, so you could maybe filter out pairs of bodies that otherwise would overlap because something about your game state has changed. Or between the narrow phase and the solver, you can modify contact points. So you could say, oh, I happen to know that bodies that have this particular tag, I need to modify the normals of the contact on them to some value or other. And so that's something that you can do then before it gets past the solver. And then kind of any time after the solver has completed and before the end of your frame, you can schedule collision event jobs or trigger event jobs. So that's what you would expect. It's just responding to different contact or overlap events and having different aspects of gameplay or audio effects or things like that play out. All right, so I'm sure everybody feels like, wow, this runtime data protocol sounds really cool when you describe it that way. How do I make content for this? So the thing that's nice is because we have a common runtime data protocol, it means we can also have a single authoring format that works for any physics backend. So if you are kind of new to DOTS, maybe if you were listening during the keynote, Joachim had emphasized that one of the chief differences between the world of DOTS and sort of classic game objects is the separation between authoring data and runtime data, right? So the types of characteristics that make runtime data good are very different from the characteristics that make your authoring data good. You want your runtime data to be sort of like minimally descriptive of the thing that you need in order to perform some operation. You want to be able to stuff it into a nice linear array and work on it in order. Whereas your authoring data, you want that to be kind of human readable. You want to be able to discover your features. You want it to actually be able to diff and merge well in a version control system. So the way that we accomplish this is that we have custom monobehaviors or classic components that we run through the game object conversion pipeline and turn into entity data. And as I said, if this is something you're interested in, I think Nicolina's talk on the design aspect or Fabrice and Simon's talk on the underlying guts of this could be of interest. But you can try this out pretty trivially if you have existing content, right? We have this concept of subscenes and convert to entity. So you can take something where you've got existing kind of classic game object and physics components on it and just convert it. And I'll show you a quick example of that right now. So we have, this is one of our learning examples. We've got this little marble puzzle thing And you'll see if I press play, it's just going to go down the chute here as you would expect. So how do we get this to work with Unity physics? It really is just as simple as taking our hierarchy here of static colliders and our marble and just putting convert to entity on it. And if I go into the entity debugger here, you'll see that I'm not lying, that there are actual entities being simulated here after I press play. So if we look at BuildPhysics World here, we've got 23 things here in our static world and then one dynamic body. And you saw all these bounding boxes appeared here as well. So we have this debug visualization system in Unity Physics that lets us look at things like the collision volumes, the contact points, and in this case what we're looking at is the broad face. So we've got these yellow bounding boxes around our static bodies, and then this, if I can zoom in here, a red bounding box here around the dynamic body. And then if you're doing this in a more complex scene, you might want to take your static geometry here and pick this new subscene from selection option. So what this does is it actually lets you do the convert to entity offline. So this is what we did in Megacity, so that all of the entity data is actually ready to be loaded in memory right away. All right, so that's great. I can use existing colliders and rigid bodies and stuff like that, but what about the new features? How do I take advantage of those? So our general philosophy behind dots is that anytime that we have sort of an existing component that encapsulates all the functionality in the new runtime, we'll build conversion systems around that. But if we have new features in the runtime that don't exist in some of these classic components, we need to build new custom authoring components. And physics was kind of one use case that fell into this. So for example, in classic Unity, you have this rigid body component, and we now have this physics body authoring component that it describes some similar data, but also exposes new features that we have. So for example, you can have per body gravity factor, as I mentioned. So an individual body, instead of just having gravity or no gravity, it can have negative gravity or scaled gravity, if that makes sense for your game. You can define kind of a custom inertia space, so you can override your center of mass and the orientation of the mass. And then, as I mentioned before as well, you can define these custom tags on a per body basis so that you can have additional sort of metadata in your performance critical code paths. In terms of colliders, we now have this PhysicsShapeAuthoring component. So before, in kind of classic Unity, you would have box collider, sphere collider, capsule, mesh, and so on. And now instead we have a single type, and it has this drop down here where you can actually pick the shape type that's on it. And the thing that's nice about this is that if you're modifying some content, let's say you're setting up a hitbox on a character, you might decide, okay, well, a capsule isn't really ideal, I want to change that to a cylinder. Then you can just swap this here, and we do a good job of actually preserving the volume of the work that you had. So you don't have to sort of reconfigure this shape altogether. And the other thing that's nice about this is that we have a couple of additional primitive types here that didn't exist before. So for instance, you can pick a cylinder, and that's going to automatically generate a nice convex hole for you based on the input parameters. You can also offset a primitive's orientation. So in classic GameObject-based physics, if you needed to have some collider that was rotated with respect to its body, it had to be on a child game object in the hierarchy and actually rotated. Now you can actually just specify an offset orientation on the shape itself. And then we also expose collision filters here on a shape. And this is kind of taking the place of the layer-based collision system that we had previously. And because it is a little bit different, if you're not familiar with this, I want to talk about this a little bit. So before, with classic GameObject-based physics, an individual game object could only belong to one layer, right? And we're using these layers for a lot of other things too. The UI system uses it for raycasting, the rendering system uses it for culling, and so you could very quickly run out of layers to set up collision behaviors that you would need. And it was also problematic that if something is a member of a particular layer, it's opting into all of the behaviors of that layer. So by virtue of saying, for instance, this collider represents a body part, it then has all the characteristics of all body parts. So if you had a particular character where you said, well, this specific body part on this character, it needs to behave like a body part for the most part, but it also needs to react to this other thing, or it needs to ignore this other thing that's different from body parts. So in order to express this now, we have these collision filters where you can specify the categories that an object belongs to and the categories that it's going to collide with. So instead of being a member in a single category, right, a single layer, you can be a member in any number of these 32 categories. And then respectively, you can collide with any number of those 32 categories. So when we have an overlapping pair of bodies, we basically are comparing, does the membership of this one body intersect with the collision response of the other body, and then vice versa. And if they both have a match, then we're going to generate a collision response, and then if you've opted into collision events, you would get those as well. Some other nice enhancements that we have with the PhysicsShapeAuthoring component compared to the classic colliders are that we can bake skew into the primitive shapes. So with classic game object physics, if you had like a box collider or a capsule collider on something that was in a hierarchy with non-uniform scale, you would get a result kind of like this one on the far left, right? Which I can't imagine a world in which that was actually the designer's intent. So what we can do now during the conversion process is reason a little bit more about what you might want to be doing. So you still get the performance benefits of having a primitive shape, but we've actually baked it out to better match the geometry from which it was coming. Another nice thing that we can do now is we can actually generate automatic convex holes and meshes from rendered geometry. So traditionally, you might have to put a mesh collider on any number of nodes in your hierarchy and maybe even assign a custom collision mesh if you wanted to have a convex hole. And we can generate that all on the fly now. And we can do that for skin meshes as well as for static meshes. So if we take a look here in the background, we have this potted plant, for instance. So it consists of both a pot and the leaves here. So if we add this physics shape component to it and we say we want this to be a mesh, it will generate a mesh collider from all the rendered geometry in the hierarchy then. And then you can do the same thing as well for a convex hole. So if we say we want this to be convex, it'll generate that from the render mesh. So the thing that's nice about that too is you can just have kind of arbitrary hierarchies of rendered geometry and say, give me a convex hole for this. And you don't have to worry about then authoring a custom mesh to do that. And then in terms of characters, as I mentioned, we can do the same thing for skin geometry. So if we have this guy here, and let's say I want to get everything except for that pot. You can see right now, hopefully, this guy has a bunch of capsules on him. And by changing to a different shape type, as I mentioned, we can kind of preserve the volume of what was there. You can easily say, oh, well, I need this to actually be a box. And maybe now that it's a box, we don't have this constraint of a uniform radius along one axis. So what we can do is we can refit it to the render meshes and maybe get kind of a tighter fit. Or you could even say, I want this to be convex holes. And we'll automatically generate convex holes based on the vertices in the skin mesh that are influenced by the particular object with the shape component and its children and so forth. All right, so we've talked a lot about, we've got these new authoring components, we've got the classic components, we have these runtime components. What are the things that actually turn into the different things? The majority of the runtime data is going to come from either a physics body authoring component or a rigid body here, right? So it's going to produce physics velocity and physics mass, and then based on the options that you've set, maybe it'll also add a damping component, a gravity factor component, or a custom tags component. Very similar story for the legacy rigid body, except as I said, we didn't have this concept of custom tags, so if that's a behavior you need, then that's not something you can achieve just by converting existing content. You need to start migrating over to the new ones. So in the case of shapes, it's a little more complicated in that they might produce a physics collider. And what I mean by that is that specifically, not everything that has a shape component is going to get a collider component on it. We want to turn these into compound shapes. So when I say maybe here, if you imagine that we have a hierarchy of authoring data, like what's shown here on the left, you could have some parent game object, and it has, let's say, 3 children here, and the 3 children have a physics shape component on them. Well, the first thing that happens when we convert these is we go up the hierarchy to find out what's the actual body that these shapes belong to. So they'll go up to the parent, and if the parent has an explicit physics body component or a static optimized entity component, then we recognize, okay, the intent of the prefab designer here, or prefab author, is that this is the body, and we want to assemble all of these shapes into a single compound on this. And then if we don't have an explicit body or a static optimized entity component, we basically keep walking up until we don't find any more shape components. So sort of the top level shape component implicitly becomes the body at runtime. So we assemble all of these into colliders that become a compound, and so there's only a single physics collider component then added to, in this case, the parent entity that we've identified as the body. So in looking at this, you might think, well, that's kind of confusing or non-intuitive. Like, why would I actually want to do that? Why does it matter to make compound colliders? So let's imagine a really basic scene here, something like we've got some vehicles and some static geometry. If you think back to the BuildPhysics World system, I mentioned that we have a dynamic entity group as well as the static entity group here. So these both exist in separate trees in the bounding volume hierarchy that's used by the broad phase and the collision world. So if we have these two dynamic bodies, maybe they consist of their bounding boxes here sort of forward projected based on their current velocity, and then those exist within some larger bounding volume, right? So this is the entire bounds of our dynamics, our dynamic entity tree. Basically encapsulates these two things plus their forward motion. And it's a similar story for static geometry here, right? So we might have these bounding boxes for all of these shapes, and they might exist in a hierarchy here where, well, the trees are some node in this and everything that's above ground, and then that's all nested under this root that contains all the static geometry. If you create a compound collider, you basically generating this information about the bounding volume hierarchy ahead of time. So if you just have a bunch of, let's say, loose static entities out in your scene, then anytime that any one of those moves, you have to rebuild the whole static tree. And you don't want to do that if you can avoid it. So the thing that's nice about building a compound collider is that you can have like a huge chunk of a tree already ready to go. So it's relatively inexpensive to rebuild the broad phase if you already know that. So in the case of the dot sample that we showed during the keynote, for instance, the entire environment is just a single compound collider. And the reason why that matters is because we have all these hitboxes on the characters that they're not simulated with velocity and all that. They're just part of this collision world for querying. So that means that we're kind of constantly thrashing this static tree. But because the entire environment is just a single body, then that means we just got one position, one rotation, and one pointer to a collider for the entire environment. And it's relatively inexpensive then to rebuild it. And I can show you, if we go back into the project here, an example of that. So if you remember, let's get this guy out of here. We had all of those, maybe if I zoom in here a bit. We had all those individual yellow bounding boxes around each of these bits. So if we instead take this static environment here and we do, let's say, static optimized entity on this. So as I said, this is one of the things that indicates to the conversion system that we want this to be a single body with a compound collider. If I press play now, instead of having all those individual yellow boxes, I have a single large yellow bounding box here because now the whole environment is a single compound collider that has its own internal tree structure. So, it still collides and evaluates the way you would expect, but it's then represented as a single rigid body for the purposes of the physics world. All right. Now, if I can read all your minds, I know you're all thinking, this is probably the best session all week. It's all downhill from here. Tell me more about Unity physics. What's coming next? I would love to tell you what's coming next. In the near term here, we're really focused on kind of getting workflows for all of the core component types, right? So as it stands today, we have all the joints represented in the runtime, but we don't have authoring components or tooling around those yet. And part of the reason is because they're actually a lot more sophisticated than the types of joints that you could create before with our GameObject-based physics system. So that's going to be something that'll be coming in the near term here, as well as some improvements to the debug visualization and performance. So, the thing I was showing you here where you can visualize the bounding boxes and so on, we want to make sure that that scales to really large environments and you don't take a significant performance penalty when you want to try to debug aspects of your physics. We're going to be working on some improvements to workflows around collision filters and materials so that you get better feedback ahead of time about what things will I expect this object to respond to and what things will it ignore. And we're going to add some data interfaces for mutating shapes at runtime. So today, if you want to, let's say, change the size of a sphere collider in your job, you have to write unsafe code, like get a pointer to this thing that's supposed to be immutable data and muck around with it, and that's not really the way that we intend for people to be working. So we're going to add actual data interfaces to this, so it works like any other component data, right? You would have a sphere geometry struct or something like that, and you can modify that in a job, and then it'll all get picked up by a system and modified accordingly in a safe way. We'll also have some stability improvements coming to the simulation in Unity Physics. So I mean, everything else here is to the benefit of both Unity Physics and Havok Physics, but the simulation improvements, that's going to be specific to Unity Physics. And then finally, we're going to be working on some usability scaffolds for the query and event APIs. So anybody who's working with dots today, you know that there's a lot of boilerplate to write your own jobs or systems. I mean, Lucas touched on this during the keynote. Now with Unity 2019.3, we have the ability to do code gen, as he showed. So we have something that looks like an anonymous method that would generate garbage, but we can actually at compiled time generate reasonable code from that that's going to perform and do what you would expect. So being able to express some collision response, it's going to look something more like the example down here, where it would say like, oh, I want to overlap a sphere, and within that sphere, I want to find all the entities that have a health component, and then iterate through those and maybe add health or remove health or something like that. So beyond those things, our focus is really going to be on nailing ragdoll workflows. So that's everything from characters to vehicles to props, and making sure that this plays well with animation and runtime rigging. So I had mentioned there's the talk on runtime rigging. That's another topic that if you're interested, you might go check out. But the idea here is that we want artists and animators to be able to set up and add physics to their characters easily, and also kind of on a per animation state basis be able to select if they want things to be simulated with physics versus using keyframed animation, and blend in and out of these as they would expect. So with that, that's all of my prepared remarks. If anybody has any questions, we have, looks like about 8 minutes here. If your questions are really difficult, I'm going to invite Steve to come up here and give you a nice ambiguous answer. I don't know if we have a microphone. Oh, thank you. Yeah. Okay. Yes? Yes? Okay. So the question is, when you're creating a compound collider out of several children, if they have to all share the same collision filter. And no, that's actually not the case. So each individual shape in that hierarchy, right? Like we're making one compound out of this right here. But if I were to, let's say instead of a capsule collider here, I had a physics shape component, this particular shape here individually can have its own collision filter specified. So you can even have, let's say in a compound collider, some of the leaf nodes might be triggers, some of them might be colliders, and some of them might have different response parameters. Yes? Okay. Triggers? Okay, yeah, so the first question was if people have to, let's say, buy Havok to get access to that. And Steve is going to be talking about that in the next talk. But for people who are using Personal and Plus, I believe it is free. And for Pro customers, it's going to be $20 a month per seat. But I think there's going to be a free trial through up until January or something like that. But it's available today, so you can go download it, try it out, see if it makes a difference for your game. Your second question was the concept of triggers, where that exists. So if you look at this physics shape component here, it's much like before. So if we're converting a classic collider here, you can say that it's a trigger, just like you would expect. If we're converting one of these, the new ones here, we have the same thing. There's an isTrigger checkbox. And when you do that, you see some of this other stuff goes away, right? Because there's no concept of restitution or friction on a trigger because it's just a volume now. So, yep. There's a question. I think I saw you stand up first, gentleman in the glasses. You might have to come closer. I'm sorry, there's a bit of ambient noise here. Okay, good question. Yeah, so the question here relates to 2D physics in the world of dots. And I don't actually sit close enough to give you like specific information of the status there. The general feeling here is that we want as much of the workflows and the components to be shared as possible. And so I think what I'm going to expect is that we'll probably have, just as we have the Havok solver and the Unity physics solver, we'll have a solver in there that's optimized for the 2D use case. And that as much as possible, we're going to share all of the tooling the way through. But I think I'm actually supposed to have a meeting with people next week and find out what the plan is there, so I can't say anything more specific right now. Was there a question down here? Here, sorry, acceleration? Oh, hardware acceleration. You mean like on the GPU, for example? I think that's probably a question that's better directed at one of the Havok folk. I don't know what the story is or what the plans are around that. But I would say maybe just catch Steve if you can't hang out for his talk. Yeah, so you can, so the question here was related to raycast. You can cast rays from a job. Basically, anytime after the collision world has been built, any job you can cast rays or shapes or anything like that. Yeah?
Where will events that arise from the physics simulation be handled in the new situation with the ACS and dots? I mean, when there is no object there, is it handled in the authoring component?
So you're asking about kind of creating collision response. So maybe an example would be I want a footstep to play when a foot contacts the ground. Yeah, so the way that we do that right now, we have the, it was the eye collision event jobs. I don't know where that is on the slides here. Yeah, so it's basically a custom job type you can create from any system and just schedule it after physics is finished. And what you get in this job is kind of a body pair. And then it's up to you in there to sort out, like, okay, does it have these components that I'm interested in maybe? And if it does, then I need to play this sound effect. So yeah, I mean, it is possible, and that's the way to do it right now. And then I think the thing that I would expect here, as I said, is that we're going to make the process of writing that code a little less painful because it just requires a lot right now. Yeah?
2 quick questions.
Yes?
One, for doing editor tooling and editor integration, can we read back all those bounding boxes that are being created, the different colliders and all the settings on that, or is that opaque to editor tooling?
So the question is whether you can also write your own editor tools that take advantage of that?
Integrate with that. So you're already generating those things and switching back and forth between different types of colliders. Can we read that back and make sure other tools are then in sync with that, essentially?
Well, so I mean, we have, like, on the authoring component, right, like, there are public APIs you can read from it and say, like, what is the shape type on this? And if it is, let's say, a box, then there's a method on it that's like get box properties. Yes, yeah, and it'll give you kind of the minimum set of data for whatever type of shape it is.
Cool. And the second one is, you mentioned that there's stuff coming to do with joints.
Mm-hmm.
It's probably getting some kind of overhaul by the sounds of things. Have you any idea of how soon that's likely to happen?
Right. So the question is kind of how soon we will have authoring representations for the joints. I would expect that's going to happen in this last quarter of the year here. And if it isn't, you should complain at me on the forums. So.
I have the same question for ragdolls.
For ragdolls, yeah.
Yeah, what's the timeline look like for ragdolls?
I mean, we don't have specific dates. I think so in terms of ragdolls, like, there's kind of some individual pieces here, right? So part of it is getting reasonable defaults for collision geometry. Part of it is being able to modify the collision geometry in a usable way, right? So I want to be able to grab one part of this and symmetrically update the other side, maybe if I need to modify the shapes, and then likewise for the joints. And so I think in terms of, what it means for it to be done, that's one question. I think that, definitely by GDC time, we should have a reasonable story around setting up ragdolls. I think there will still be ways to improve it, And I want us to be really aggressive about that so that it's, I mean, you saw on the character here, it's a matter of like I add these shape components and they're automatically sort of initialized based on the geometry in the skin mesh. So it's kind of like that's already, I think, an improvement over the existing ragdoll wizard that we had. But I think I want it to be something where it literally is just a matter of there's a checkbox on the importer to generate all the ragdoll parameters. You get it, and then you can make modifications if you need to. But you know, in terms of the timeline that all that's going to play out on, I don't know specifically. We'll see how it plays out. I'm being told we're out of time. So all of you who have more questions, I'll still be out here in the hallway, and I'd love to chat with you. Otherwise, I hope that people who are interested stick around for Steve's talk. Thank you.